All right, now let me read problem number 3. It's very similar to number 1. It says a 2.5 nylon fishing line is used to hold up an 8-kilogram fish, and it has a diameter of 1.6 millimeters. How much is the line elongated? Now, elongated is a fancy word that means stretch. So let's draw the picture. I don't know, maybe this is like that's the lighthouse. And here's some guy fishing. And he has a fishing pole. And that fishing pole has a line. Okay? Now, what they tell us is that, let me read this again. I drew my picture. It's a 2.5 meter nylon fishing line used to hold up an 8-kilogram fish. So the length is 2.5. The original length is 2.5, right? And it's holding up a fish whose force or mass, its mass is 8 kilograms. So there's a little fishy here. Okay. And he weighs 8 kilograms. That's a pretty big fish, actually, when you think about it. 8 kilograms is pretty big. All right. So then the question that they asked us was 2.5 milliliter or 2.5 meter nylon fishing line holding up an 8-kilogram fish. Also, the diameter of the line, if we were to look at the line, the diameter of the line is actually equal to 1.6 milliliters, or millimeters, I mean. Let me read it here again. 1.6 millimeters. 1.6 millimeters. Now, that's the same as 0.0016 meters. So we want to convert everything to meters, kilograms, and stuff like that. And so the question that they're asking us is how much is the line elongated? How much is it stretched? All right? Well, now here's the interesting thing about the fish. This is pretty much the same problem that we did for problem number 1. Right? So this is going to be Young's modulus is equal to the force over the area all over the change in length, which is what we're looking for, all over the original length. All right? The problem is we might need to do a little more calculation. Well, this fish has a mass of this, but what is the force? Well, we have to make some assumptions. 2.5 meters isn't very long, so let's assume that the fish is out of the water and he's reeling it in. What force is that fish going to have on that line? Well, force is equal to the mass times the acceleration. So if he's reeling in that fish with his fishing rod, and the fish is no longer in the water, what is the force that's being applied? It's 8 millimeters times an acceleration. What acceleration is being applied to the fish? The acceleration due to, which is 9.8 meters per second squared. So I'm going to say 8 times 9.8. Okay? And that will give me the force. I'm going to do something a little different for this problem that I didn't do on the last problem. I'm going to take this formula. We're really just interested in this. So let's solve for delta L first, then plug the numbers in second. Can we do that? So delta L then, if I were to, I want to get rid of delta L. So one way to do that is to multiply both sides by delta L over L naught, right? And if I do it on one side, I got to do it on the other side. Now when I do that, I get delta L all over L naught times gamma is equal to F over A. You guys with me so far? Now I could rewrite this like delta L times gamma over L naught equals F over A. Right? I could write it that way, couldn't I? It's the same thing. That makes sense so far? So now what would I do? Well, if I want to get rid of this, I have to multiply by the reciprocal. So I would say L naught over gamma. Whatever I do on one side, I got to do on the other. L naught over gamma. Now what happens is this cancels with this, and I get delta L is equal to, whoops, that L wrote up a little high there. Delta L is equal to F, the force, times L naught all over the area times gamma. Is that right? Does that look right? So let's figure that out. Well, the force we said was this stuff here, so I've got 8 times 9.8. Then we need to multiply that by the length. What did we say the length was? 2.5 meters. So that's the top part. The area was pi times the diameter, 0.0016 squared all over 4, times gamma, which from our last problem we said was 5 times 10 to the 9th, right? That was Young's modulus for nylon, was 5 times 10 to the 9th, wasn't it? So let's plug it in and see what we get. So I'm going to plug this in my calculator. I'm going to do it step by step though. So I'm going to say 8 times 9.8 times 2.5, and that gives me 196. So delta L is equal to 196. Now this bottom line is going to be kind of tricky, so let's see how we do with that, okay? I'm going to have to say pi times, then in parentheses I need 0.0016 squared, right? I'm going to divide that by 4. That's my force. And then I have to multiply that by 5 times 10 to the 9th power. So I get 10,053.0, 10,053 what was the rest of it? 0.9. Let's just say 0.1. We'll just round. 0.1. Is that right? Well, let's see what that is. If I say 196 divided by whatever my answer from the last one was, I get 0.019 meters. 0.19 meters. Now, if I were to convert that, it's actually 1.9 centimeters. You could write it that way. That's what the answer in the back of the book is. Right? Is that right? So what does that mean? I'll give you guys a second to write that all down. What that means is, as soon as I reel in that fish, the original length of the line is 2.5 meters, but as soon as that fish breaks from the water and gravity is pulling on the fish, my line that's supposed to be 2.5 meters stretches just a little bit because the fish is pulling it down. And that little bit that it stretches is 1.9 centimeters. Does that make sense? Anybody have any questions? Now it's still nylon, right? What that means, there's millions and millions and millions of molecules that are kind of sticking together from the various bonds that holds the nylon in place. Because nylon isn't an element, right? So there are a bunch of atoms that are arranged in a certain way and they stick together. So the force of the fish, as you apply it over all of those atoms and molecules, it stretches out just a little bit. And if you add all that little bit up, it comes to 1.9 centimeters. The diameter changes a little bit too. Okay? That's it.